quicker than the texture of space-time can stay aware of it, and it'll simply tear. I'm alarmed by this. As of now, our evening sky is changing quickly, and in a matter of many years, if not sooner, it may turn out to be totally unrecognizable. Cosmologists overall are sounding the alert. Specialists like Neil deGrasse Tyson have recently affirmed the inevitable blast of Polaris, and the tale behind it is very startling. Polaris, known as the North Star, has for some time been a constant in our night sky, filling in as a vital reference point for stargazers, pilots, and navigators. However, this could soon change, modifying our night sky and cosmic estimations. We should dig into the meaning of this threat and its implications for us all. Join us as we uncover the narrative of Polaris as it approaches its end. For centuries, Polaris has guided sailors and stargazers alike, standing firm on a venerated footing as a guiding light. Its steady presence in the night sky has been fundamental for navigation. Yet, this stability may soon be upset. In September 2023, a research paper introduced by the esteemed Royal Astronomical Society cast doubt on the fate of this celestial light. Polaris is near the precipice of detonating, potentially evaporating from the night sky forever. Before we investigate the outcomes of this discovery, let's learn more about Polaris, otherwise known as the North Star or Pole Star. Polaris is unique due to its closeness to the celestial North Pole. Positioned almost directly above Earth's North Pole, it appears nearly fixed in the northern sky, within the constellation Ursa Minor or the Little Dipper. Polaris shines as a relatively bright yellow-white supergiant star, much larger and brighter than our Sun. It's not a single star, but part of an intricate triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris C orbits them. The interactions among these stars create gravitational forces, shaping their orbits and affecting their behavior. Any disturbances in these interactions can lead to irregular variations in the star's brightness or pulsation patterns. However, the exact details behind these connections remain unclear. Polaris is located about 323 light-years from Earth, meaning the light we see from it today began its journey over 300 years ago. Consequently, if Polaris were to explode now, we wouldn't notice it until more than 300 years later. It's even possible that Polaris has already exploded, and we are yet to witness the light from that event. Since ancient times, the North Star has held significant cultural, navigational, and symbolic importance. Its stability and fixed position made it an invaluable guide for ancient navigators, directing them across oceans and lands. Symbolically, Polaris represented constancy and direction, remaining steadfast amid the ever-changing night sky. For astronomers, Polaris has served as a crucial reference point, aiding in the study of celestial movements and variable stars. As a Cepheid variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a key role in determining vast distances and calibrating instruments. These pulsations follow a predictable pattern, which has been the norm for the star, making it easy for us to anticipate its behavior. However, recently Polaris has strayed from this usual behavior. This anomaly in its pulsation cycle has puzzled astronomers, prompting closer investigation of this celestial oddity. Instead of its regular predictable pattern, Polaris has begun to show irregular patterns of dimming and brightening. Researchers are now raising concerns that the star may be nearing the end of its life. This lines up with behaviors commonly observed in stars approaching the end of their life cycles. The steady lengthening of Polaris's pulsation period, which was once stable, can be attributed to interactions within its star system. We've observed an annual increase in its pulsation period of 4 to 5 seconds. While this may seem insignificant, it has profound implications. Some astronomers propose that gravitational interactions between the Polaris stars could be causing these changes in its environment, directly influencing its pulsation patterns. However, others are more concerned, fearing the star is on the verge of exploding. The similarities between Polaris's behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have exhibited puzzling irregularities in their luminosity, raising concerns about potential explosions. Cepheid variable stars in their twilight stages often show such inconsistencies before reaching the peak of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been officially directed toward Polaris. As a Cepheid star approaches the end of its life cycle, it goes through several stages, including the main sequence stage, red giant stage, and, ultimately, the supernova explosion. Based on Polaris's unpredictable pulsations, scientists predict it has entered the stages of helium fusion typical of Cepheid stars nearing their end. These anomalies in Polaris's behavior align with patterns indicative of Cepheid stars in their twilight stages. However, conclusive signs of its impending supernova remain uncertain. If Polaris were to go supernova, it would likely be an extraordinary event in our sky, potentially eclipsing the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance could dramatically alter our view of recognizable star formations like the Big Dipper or Ursa Minor, of which Polaris is a part. However, the Earth would likely be completely safe, even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually spectacular as that of Betelgeuse, it could still be visible to the naked eye for an extended period and dominate the nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers worldwide. However, the specific visibility and effect on Earth's climate or environment would be less significant compared to a closer supernova event. But what about Polaris itself? What will be its fate after a potential supernova event? Let's clarify one thing. While massive stars typically end their lives with a supernova explosion, this is unlikely to be the case with Polaris. When a massive star goes supernova, a massive explosion occurs within it, marking the final catastrophic stage of its life. This process involves a complete breakdown of the core, triggering a violent shock wave that causes the star to explode. However, Polaris isn't massive enough to go through such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transition will not result in a supernova but rather a peaceful end as it evolves into a small, incredibly dense celestial remnant. A white dwarf is the leftover of a low or medium-mass star that has used up its nuclear fuel. It's extremely dense, about as massive as the Sun but packed into the size of Earth. When this happens, we will no longer be able to see its remnants from our planet, just as we can't see the star today. Comparing the expected effects of Polaris's explosion with historical supernova events gives us valuable insights into stellar evolution and their ultimate fates. Comparing our expectations with actual supernovae like SN 1987A and later events such as SN 2011I or SN 2014J offers important data for understanding the possible outcome of Polaris's burst. For example, SN 1354 led to the formation of the Crab Nebula, a cloud that continues to expand and emit radiation across different wavelengths, providing astronomers with a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, gave insights into nucleosynthesis processes and the dynamics of supernova remnants. Investigating anomalies like the formation of nebulae, the release of cosmic rays, and variations in luminosity can offer clues into Polaris's unique characteristics. The development of nebulae, like the Crab Nebula, results from the expulsion of material during a supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavier elements and contributing to the process of stellar birth and death. Additionally, the release of vast beams of high-energy particles, accelerated by the supernova shock wave, has implications for astrophysical processes and cosmic radiation conditions. To make a definitive comparison, researchers assess differences in mass, composition, and speed of ejected material between Polaris's potential burst and other observed events. This includes analyzing light curves, spectra, and remnants from these events and projecting similar attributes for Polaris's expected burst. Another important area of investigation involves studying the pulsational variability of stars approaching their end stages, such as Polaris, in comparison with known supernova progenitors. This comparative study helps gauge similarities or deviations, providing insights into the burst mechanism. Pulsational instability in stars nearing the end of their lives may be indicative of internal pressures or impending catastrophic events, offering clues about the evolutionary processes leading to supernova explosions. Despite meticulous observations and extensive research, astronomers remain puzzled by the anomalies seen in Polaris's behavior. Unraveling the extraordinary conditions driving these irregularities holds the key to advancing our understanding of stellar evolution. Understanding the mechanisms responsible for Polaris's unpredictable pulsations requires interdisciplinary collaboration, as well as the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a major reference point in the night sky raises significant concerns for astronomical missions, ground-based telescopes, and celestial measurements. These would require recalibration, affecting the accuracy of astronomical evaluations. The absence of Polaris could also impact navigation systems and cultural practices based on celestial landmarks, underscoring the importance of this cosmic event. The puzzling behavior displayed by Polaris highlights the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its irregular pulsations and present concrete answers, recognizing the significance of advancing our understanding of cosmic mysteries. Ultimately, the answer to Polaris's fate remains uncertain, and only time will reveal its true nature. Nevertheless, the pursuit of knowledge and understanding, even in the face of immense uncertainty, is a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. The expected fate of Polaris raises fascinating questions about the future of other celestial bodies. As we observe these changes, astronomers are constantly reminded of the dynamic nature of the cosmos. Stars like Polaris and Betelgeuse are only two examples of the many stars that undergo dramatic changes, offering valuable insights into stellar evolution and the life cycles of massive objects. Beyond Polaris, many stars exist in similar evolutionary stages. Some are in the later phases of their lives, displaying extraordinary behaviors that could signal impending changes. For instance, some red giants exhibit signs of instability, fluctuating brightness, and erratic pulsations. This variability often serves as a warning signal, indicating that the star is running out of fuel and moving toward the end of its life cycle. Such stars become laboratories for astronomers studying the mechanisms behind stellar evolution and explosive phenomena. In addition to studying individual stars, scientists focus on star clusters, where many stars form and evolve together under similar conditions. Understanding how these stars interact can shed light on the environmental factors that affect their life cycles. The dynamics within these clusters can lead to fascinating phenomena, such as the transfer of mass between stars, which may eventually alter their evolutionary pathways. Furthermore, the study of supernova remnants, including the leftovers they leave behind, provides a wealth of information about astronomical events. When massive stars explode, they release vast amounts of material into space, enriching the surrounding interstellar medium with heavy elements. This material can contribute to the formation of new stars and planets, highlighting the interconnectedness of the universe. The remnants of supernovae often manifest as nebulae, which act as stellar nurseries where new stars are born. Observing these processes allows astronomers to piece together the cosmic puzzle of birth, death, and rebirth among celestial bodies. The implications of these stellar explosions extend far beyond the immediate vicinity of the event. Supernovae can impact star formation rates in their regions, influencing the development of entire galaxies. The shock waves produced by these explosions can compress nearby gas clouds, triggering the formation of new stars. In this way, the life cycle of a single star can have a ripple effect throughout the universe, shaping the development of galaxies over billions of years. As technology advances, astronomers are increasingly able to monitor and study these cosmic phenomena. Space telescopes and ground-based observatories use sophisticated instruments to capture detailed images and spectra of distant stars. Data from these observations help researchers build models that simulate stellar evolution, making predictions about the behavior of stars like Polaris. AI and artificial intelligence are also playing an expanding role in this field, enabling scientists to analyze vast datasets more efficiently and uncover patterns that were previously overlooked. In addition to understanding the physical changes within stars, the societal impact of celestial events should not be underestimated. Throughout history, astronomical phenomena have influenced human culture, mythology, and navigation. The North Star, for instance, has been a symbol of direction and hope for countless generations. As our understanding of the universe grows, so too does our appreciation for how these events shape our shared perspective on the cosmos.